We are back with day 10 of 30 days of machine learning. It's been a very exciting past 2 days. We discussed ensemble learning from scratch on day 8, and yesterday we implemented the entirety of XGBoost with the derivation. Very exciting video to check out, and there's lots of articles attached as well that you can always read, and I will make sure to attach some articles in the description of this video as well. And without wasting any time, let's move on with today's problem statement. Okay. So what do we have on our hands today? Rossmann Store Sales Forecasting. Yeah. Very good, actually. This will be a very good problem statement. Again, tons of concepts attached to it. So Rossmann is nothing but the name of a store, and basically the question that's given to us here is that we have got the sales data, the historical sales data of some customers, dependent upon lots of dependent features, and basically our task in here is to use the historical data to predict the sales done by the Rossmann store on some new data, which we'll basically be taking as the testing data. So a pretty simple problem statement to analyze, okay? And of course, by just reading it, we can say that this is nothing but a regression kind of a problem statement, because we are given some values x and we are supposed to predict some value y from it. So it is sort of understandable that way. So keeping that in mind, that this is basically a simple regression problem, we move forward. So, you can read this alongside, you can read it later. This is available in the repo readme itself. Okay. So there are a lot of Rossmann drug stores, 1,115, across which we predict the daily sales. That is the task that has been assigned to us. So again, we have to build a very robust, a very generalizable regression model. Okay. Uh, these are the input features that we have. So you can let me do this for you. Basically, you can do this later as well. The data set that we have used is available on Kaggle, so you can use it. This is the training data, and then this is the store data. You can store it in Kaggle, and you can download it from Kaggle and you can use it. So this is how the data is going to look like. Now this is sort of incomplete data, because it just looks like this. This is incomplete, which is why you have to download two separate files for this specific problem. This contains the information about the store, and this contains the information about the customers basically. So, this is the customers, okay? The sales, then we basically have got whether the store is open or not, promo, state, holiday. So these are all very important features, and both of these files give us very important data using which we train the model eventually. Okay. And yeah, one thing that I wanted to tell you, this is a massive data set. Again, I mean, we will deal with even bigger ones later, but till now, I think this is the biggest data set we are dealing with. It is nearly 1 million samples. 1 million is 10 to the power 6. See, it is more than 1 million. Okay, so there are tons of samples in here to deal with. And this is again the other store.csv file. Both of them are used. Okay, so it's pretty simple to go forward with. Now, once we go on with we go on to train the problem. Now, we go on to train the model with the standard steps that we do. So one thing that, should be clear by now, which we can confirm later as well, is that the relationships in this model among the different features are non-linear. What does that mean? So let me quickly get to the board to explain it. So, imagine we have like a simple problem on our hands, like a simple regression problem. It can be anything. So what happens in a simple regression problem is that, yeah, okay. So, what happens in a simple regression problem in general is that, we get something like y is equals to m x plus c. This is what we get in any simple regression problem. Okay. And basically, the idea is that this x are the features. the historical data that we have been assigned with, the data set features. And using that, we have to predict the output Y. And output in this case is nothing but the daily sales of the Rossmann drugstore. Okay. And this is nothing but the historical data on which the store sales are dependent. M is the slope. This is basically the equation of a line. M is the slope and C is the insight. So guys, we have got the sales. This is how we predict. But the thing is, guys, this is like a linear equation, right? This equation, let me write it down so that can just have it for a record. This is a linear equation that we are dealing with. Okay. Now, what happens in linear equations is that, of course, it captures only linear relationships. Relationships which will look like this on a graph. Like this or similar to this. Okay. This is like a linear equation graph. Okay. Passing through the origin. So this is how, or it can be like this, or it can be like this. The point is it will be a straight line, which means it is linear. But what if the data set relationships are non-linear? Okay, meaning that the data set features are not correlated to each other. They are different to each other. Let's say, it's something like a quadratic relationship. Maybe X and Y are related like this, maybe like this. We don't know. It can be anything. So, before analyzing the data, we can never be sure as to what model we should be implementing for any specific problem statement. Like in this case, if you just look at the data, it has got like 1 million rows in it, 1 million samples. So you cannot just scroll through all 1 million samples to analyze how the data is looking, what is happening. So for that, we go forward with the number one step in any machine learning pipeline, which is the which is the exploratory data analysis step. Okay. So first of all, these are the standard imports that we make. Okay. We have been repeating this a lot, so you can just look at it. I'm not repeating these things again. NumPy and Pandas, typical, what we always do. These two, Matplotlib and Seaborn, are for the data visualization part. Time we have imported because we are going to calculate the inference latency and the training time for the model. Train test split, cross is all typical. Okay. Moving on, when we go to the data set, this is how we import the data. Okay. So we have got two files here. Like I said, we have got the train.csv file and the store.csv file. So what you can do is you can, upload these files here and then copy their paths inside these ports in order to use them. This is the simplest way to run. Okay. Then this is how we import the file. Simple. Now, since the beginning, this is how we go and train every pipeline. We first analyze and understand the problem. Then we look at the data set, then the EDA, then the pre-processing. And after that, we, take all the trade-offs that we have on our hand and try and analyze as to which model would be the most suitable one. So the thing is, the pre-processing till now was like very repeated, right? It was basically the same steps that we were doing till now. But here we have some new steps. So I'm going to spend a little extra time on the pre-processing here and on the EDA. So just hear me out one by one. Okay. The first new thing that we have got to learn here is that, we always do this. DF is equal to PD dot read CSV. It is the typical step in importing, our file and basically letting pandas read it as a comma separated value file and then slowly analyzing it and moving forward. But what about this right here? What about this low memory is equals to false? What does this do? So this is a new thing and it was new for me as well. I had not dealt with this before. And this is why building models with your own hands is pretty important. You learn most of the stuff while building the model because it might be available in some literature of machine learning or some book out there, but I haven't seen it yet in a book or something. Or like someone explain it separately that this you might come across low memory is equal to false. What does it mean? So this is very important. So I'll explain it to you quickly. So let me go back to the board here. Okay. So what happens is whenever we let pandas read a comma separated value like the Excel file that we have. So imagine there's a column. Okay. There's a column in here called as I don't know anything. can be like, let's say the column is called as X and it has some features in it. It has got 1, 2, 3, it has got A, it has got NN, okay, it has got a 0, then, sorry, 0. Then in one place it is, empty. So this is, for example, this is like a column that is available in your CSV file, and your model, your is reading it in the first step. So, what happens is when you call pd.read.csv on your dataset file and it contains columns like this, it is going to assign some sort of categories to all of these independent rows. Okay. So for example, 1, 2, 3 here, if it is a number here, so it will be just written as 1, 2, 3. Otherwise, it might have been a string, and it would have been something like this. So pd.read.csv is going to assign some type to it, some data type to it, that what it is actually, to identify with it. So in this case, let's say it assigns int to the 1, 2, 3. Okay. To A, let's say it assigns the type string. To NN, let's say it assigns the type string again. For 0, again, it can be string or it can be integer. So you see what is happening. In a single column, we are getting different types of data type being assigned at every step. So for first row, it is first looking at what the entry is. So it sees, okay, the entry is 1, 2, 3. I'm going to assign int. Again, float can be assigned as well, right? Why can't float be assigned? It can be assigned. For A, it assigns string. For NN, it assigns string, and so on it moves. But the thing is that 1, 2, 3 can be both. It might be an int, it might be a float, it might be a string. Okay. So, we need to sort of avoid this, because this will waste a lot of time. And, these types of columns are always present in sales forecasting kind of problem statements. So like in today's problem statement, you will see at least one column where, these varied sort of columns are present. And, this does not lead to clean pre-processing later. So to fix this problem, we have this low memory is equals to false. Okay. And what it will do is, in general, when we don't write anything, let me quickly write it again. When we don't write anything, when I just go on and say pd dot read CSV, and inside I've got my file path. When I don't write anything and I close the bracket, it automatically assumes, by default, that this low memory is equals to true. Okay. And what this low memory is equals to true does is that, it basically analyzes the data type of each row one by one before moving forward. So like I showed it to you here. So for this row, it will first analyze the data type, then it will go to next, then it will go to next, then it will go to next. So when we write this low memory is equal to false, we are basically telling pandas that you are not going to assign a data type to each row individually. First, you are going to go through the entire file. Then you are going to assign the low memory is equal to false. Now, why is this good? Okay, why is this good? This is good because once the pandas is through with the entire file, with all of the samples or all of the rows that are present in the data set, it can get a better idea as to what data type it should assign to that specific column. Okay. So like I said that, the 1, 2, 3. Now let's say that, this column, this X column here. Now let's say that pandas assumes that this X column is having all integers. Let's say it assumes that. But the thing is that A is not an integer. So this will lead to some sort of an error. N is also not an integer. 0 is an integer, so it's fine. Or let's say it assumes that this entire column is rather represented as string. So, again, 1, 2, 3 can be represented as a string. A can be represented as a string. So this way it makes much more sense. So, this is why it is very important that first all of these rows, all of these samples are analyzed. They are looked at, they are read first, and then the type is assigned. So it is very important that we first read the entire file, then we assign the specific data types. Because once we have read the entire thing, we will have a better idea on our hands that what data type should be given to the samples inside the column. This is what low memory is equal to false triggers. Okay. It will say, oh no, 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 no. You are not going to write these data types first. You're not going to assume anything. First, you will go through all the rows. This way, you will have a better idea as to what the column is representing. Then you can say that, yeah, this column is an integer type column, or whatever categorical column you need to assign it as. So that is what this low memory is equal to false does. This is a very important concept, and these are very small things that we usually just look past, but they are actually used, and it's good to just open them apart completely and understand them. Okay. So which is why I wanted to state this. So this low memory is equal to false is used in basically uploading the path in both the files. So for the store.csv and for the frame.csv. Okay. Now, like I said that both of these files are used, so we merge them together into one. We do the left merge. Okay. Now comes the EDA. Now, like I told you that the EDA is actually the thing that gives us an idea about the massive data, because of course it will be very naive for anyone to scroll through 1 million entries. Okay, you cannot scroll through 1 million entries, which is missing. What's the distribution? It's stupid to do that. So that is what we have done. Df.head, again, this is old stuff. It returns the first 5 rows. It is just to check how the data set is looking. Dot shape returns us the number of rows and columns. I've commented it out because the EDA has no role in training the model. It is just for the engineer in question who is trying to build the pipeline for just to analyze the data set. But once we are, through and we want to deliver the final product or the final model, we don't show this. This is for us specifically, which is why I've commented it out. You can run it yourself. This code is entirely runnable. There are no bugs in it. Okay. Df.describe again gives us the statistical features that we can look at. So basically the mean, the median, the mode, standard deviation, all of these common statistical values. Okay. This gives us, how many missing values are there in the data set. This is like a very common keyword, df.isNull.sum. Okay. And we have also done this sort values. So if there were any missing values, we get them in descending order. Okay. Meaning the values which, the columns which have the maximum missing values, they get first, and then the second, and then the third, and so on. Okay, simple. And upon running this statement, we found that there are no missing values because this data set is from Kaggle. Kaggle data sets are usually not unclean. They are pretty clean to work with already. This is why this is a good data set. Okay. Now, very important. So guys, this is a very good practice you can do. So in this problem, let me quickly write it again. What are we actually predicting? We are predicting the sales by the Rossmann drugstore using some historical data. So this is what we want to predict. So, this is our dependent feature, or it is also called as the target variable. Okay. So whenever we have a regression problem, it is very good to get an idea about the historical distribution of this variable. Meaning that, I have to predict sales for the new independent features, but I don't really know as to what the distribution looks like for sales. How do sales increase with different increases and decreases in the values of the other features? How does their correlation look like? So to print that, we basically plot a his plot or a histogram using Seaborn library for the sales. So this is how we have done it. Okay. And when we print it, it comes out to look something. Okay, wait, it's not here. Yeah, just a second. So when we print it, wait a second. Why is it not showing? Okay, let me get back to the repo and show it to you. Yeah. So when we print it, this is what the sales distribution looks like. Okay. So this is the sales which have been done, and this is the count. So, you can look at it. Now, this is very important to analyze. When we look at such data sets, these are called as right skewed data sets. Okay. Meaning that the values on the left are higher, and the data set is basically, sort of this sort of a shape we make it. So if this is the standard number line, 0, right skewed data is like this sort of a data. Okay. Basically, all of the highest values, all of the peak values are lying on the left side, right here. Okay. And as we go to the right, the values start becoming extremely small. Okay, this is called as a right skewed data. If it was for the opposite side, it would have been called left skewed data. Okay, so this is not resembling the standard bell curve or the standard Gaussian distribution that we try and get, because that is very intuitive and much cleaner to work with. So for that, we have done a very good process in here. We've applied log transform to this. Basically, what we do is we are saying our data is right skewed, and it basically will give us some instability in training, because some most of the higher values are concentrated towards the left, but we don't want that. We want them to be uniform. So how do we do that? To do that, we do a very simple thing. We take the logarithmic of all the values and then we plot it again. This way, after taking log, it basically gives us a much more balanced data set, something which is, closer to our standard Gaussian distribution. So from this one, so from this right skewed distribution, it gets transformed to something like, our standard Gaussian distribution that we get. Sorry for the handwriting. Okay, that we get usually. And this is much more intuitive to work with because, all of the values and equations for this are preset. The Gaussian distribution is one of the best to work with because it is the conventional one. Okay. So this is why we have applied the log transform. If you want to look at it in the data set, you will find that we have applied it. Okay. So this is for the sales distribution. Now, very important. After the sales, we have had a correlation heat map. Now, this correlation heat map is very important in determining the relationships. So, did you see how we discussed the relationships here? That, this is how a standard regression, linear regression relationship may look like. But not all data sets are linear with each other. Features might have different relationships, different interactions with each other, which might be non-linear in nature. They might be quadratic, they might be cubic, I don't know. To figure that out, we have, basically printed this heat map, this heat plot. So this heat plot tells us that the values which are the darker squares are the most correlated. So, which is why the diagonal is the darkest, because the diagonal shows the relationship of the feature with itself. So, like, you look at this square right here, it is duration with duration. So, of course, the correlation between duration and duration is the highest, it is 1, because it is the same one. So, correlation between any two features, okay, correlation between any two features is the same, because you are saying that let's say how much is iron correlated with iron. Iron is the same thing as iron. So obviously those two things are the same. So they are completely correlated. So they have a correlation value of 1. And correlation values can lie anywhere between -1 to 1. Okay. And these values basically, one, the closer it is to one, it means the features are highly correlated. This means the features are very low in their correlations. Okay. And to plot this in a heat map, because no one wants to look at so many numbers, we rather plot the heat map, which gives us colors. So the darker the color, the higher the correlation. So you can see most of these colors are very, very light, most of them. See, it is white, orange, these are very light colors. Okay, so this basically means that there is very low direct correlation between the features, and you can read this as well. So this way we can confirm that if we use a linear regression model, or for that chance, if we use any other linear model, it will definitely underfit and it will not capture the complex relationships that we have in this data set. So we definitely need to go for a model which is more complicated than linear regression. Okay. So did you see the process, how we analyze these things? Okay. We don't just jump to a model saying that this is it. Okay, there's a specific process you need to follow. You do the EDA, you look at the data using the EDA, of course. You plot the heat map, you look at the correlations, analyze everything, see the size of the data set. Then and only then you jump to a final conclusion that, yeah, this might be a good model to start with. and then later we update the model. So let's get on to that. Okay. So now you can look at this. This is the basic feature engineering. I'll show it to you in the code as well. So what happens is that in the data set we could see that some stores were closed. Right. Let me quickly open the data set once again because it will be much easier to notice this in the data set. This is the store type. Okay, let me get the other one as well, the training one. Yeah. So you see how, okay, it's not opened yet. Just a second. Uh, yeah. So you see how in this one we have a column called as open, a feature called as open. So it mostly has the value 1, but in some places it is going to have the value 0. And I have to find it. This is a massive data set. But the thing is that this feature right here, it means that whether the store is open or closed. So tell me something, if the store is closed, is it going to have any sale? No. There are no sales. Now the store is closed. The shutter is down. They're not selling anything. They're saying, I'm sick, I'm at leave, I cannot sell anything. So wherever we have the rows where the stores are closed, basically wherever this feature right here, this open feature is assigned as 0, we drop that row completely. Okay. This is called as feature engineering. We are basically changing the features according to our own data. It just came here. I saw some values for 0. So wherever this value is 0, so it no, just a second. So we saw some values which are assigned as 0. So wherever this value is 0, this open value, it means that the store is closed, and we drop those rows completely so that our training becomes better. Okay. So that is what we have done. Let me get back to the repo. So that is what we have done. We have excluded those. The log transform we have applied in order to stabilize the variance. This is very important as well. And I forgot to discuss one small thing. If when you read this, you might think, what does this mean? Because it is written that this causes heteroescadatic noise. Okay. So basically, the right skew distribution causes heteroscedastic noise, and heteroscedastic noise means that the error variance is going to change. What does this mean? So let me show it to you again. So let's say that we are building a model and we are calculating the loss, okay, which we do in any machine learning model, and it is coming out as some value x. Next time it is coming out as let's say some value x plus y, or maybe some value like 2x. So it is somewhat related to x, and we can generalize this in the form of a loss function. But in the case of right skewed distributions, the heteroscedastic noise is added to this, and basically the loss function becomes a lot varied. It becomes unpredictable. Okay. And this causes like a major problem, which is why the log transform that we do here becomes very important. Okay. So if the log transform is not done, the noise will be added, which is not predictable, and it will lead to like tons of instability during the training. It will not lead to a good model. Okay. That's what happens. So we have got the categorical encoding, which I will discuss in the code itself. And this is simple, that if there are any missing values, we fill them up. Okay. So we go on to the feature engineering. See, open stores as one, so that if the store is closed, there is no learning from them. So we basically transform the open stores to one. We can also remove the values as well. If there are some values where the stores are closed, we can remove them as well because they're not contributing anything to the learning. In this case, we have just assigned them as one, so that all of them are one during the training and we can utilize something out of them. So we had a date column, and the date column again was not doing anything special for us. So we broke apart the date column and basically took some stuff out of it. Let me scroll back to the top. So this is the date column. So again, the date column has all sorts of different dates. So the thing is that the issue this causes, the date in itself is not that usable until we try and extract some feature out of it. Because like I said, that a machine learning model doesn't really care if you have date as, let's say, 23 5, and 15, something like this. Now, this does not make any sense to the machine learning model because the model just interprets this as random numbers and it does not learn anything from them. So to do this, we do a very simple thing. We extract this, and this separately out of the date column and then drop this column entirely. Basically, we make three separate columns, one for this date, one for the month, and one for the year. And then we remove the original column. So this is pretty basic stuff. See, the year and the month have been, separated, and then we drop this, the original column. So you can read it as well. We extract useful features and then drop the column. Okay. This is the log transform that we talked about applying in the sales. This is to prevent the heteroscedastic noise that we don't want in the model and for it to converge quickly during training. Now, once the EDA and the basic stuff is over, we head on to the second part of the pipeline, which is data pre-processing. Okay. Guys, I have not yet moved to the model, and the reason for that is the model, I will discuss it in depth. It is pretty easy to implement, but the pre-processing and the EDA carry more essence in here because we haven't dealt with such a big data before this. We were using pretty easy data sets. This is the first, million plus size of data, and it has a lot of stuff to do in it, which is why I'm trying to stress as much as I can upon this. Okay. So for the pre-processing, very important. First new step right here. What is happening here? What is this dot as type string? Okay, what is happening here? So, guys, this is pretty important. Pay attention. So, we have got different sorts of columns in here where some values might be strings, some values might not be strings. So, to make it uniform, we declare all of the values inside this column as a string. So, let me show it to you. We have got just a second. Yeah, we have got this promo code and we have got this state holiday. So you see, these are actually encoded columns. This has got 0, 1, 0, 1. Now what happens here is that, let's say that I have a column, gender. Okay. Let's say I have a gender column. Okay. And, this is like, let's say we have got multiple examples in gender. We have got male, we have got female, we have got, I don't know, there are people who will say, uh, there's also this rather not say. Okay. There's all these sorts of options. There might be even more options because people are providing them these days. So, when we try and encode this, let's say that we assign male as 0. Okay. Try to like binary encode it, or, try to categorically encode it. And we give female as 1 and we get rather not say as 2. Now, this is fine, right? This looks fine when we do it. But there's an issue with this. The thing is, guys, these numbers might form relationships with each other. Because when we go on the number line and try to look at it in the form of mathematics, we know that 2 is greater than 1 is greater than 0. And the machine learning model might start believing that, this rather not say is greater than female is greater than male, which doesn't make any sense. But this might hamper whatever learning we are trying to do in the model. So, these types of relationships cause issues in the model itself, especially when they are encoded directly as numbers. And when we go and look at our data set, like I showed it to you right now, this state holiday, this school holiday, promo, these have numbers 1, 0, 1, 0. There might be other numbers as well. And these kinds of features cause issues in our data set. So that is why we have completely transformed them to a string using this keyword right here. Okay. Do you understand what's happening here? We have completely transformed them so that, later they do not cause an issue. Okay. Then this is a good trick that we have done. We have taken all of the categorical columns separately. Okay. These are the categorical columns, which means they have got categories in them. And what we do is again, we use the dot as type function and basically we assign different categories. So this, what this will do is, let's say that, any column, let's say state holiday. We have got state holiday. Okay. And it has got, let's say 4 categories. category 0, category 1, okay, then category 2. So these categories, we have to assign them separately to different, values inside the state holiday column. So that is done by this category right here, this one. And, later, like I said, that any machine learning model, it does not really understand string. It doesn't really understand any words. So it needs to convert those words to numbers. This cat codes converts these string values to some sort of numbers, to some sort of interpretable numerical values that the model can understand. This is done by cat codes. Okay. So this is clear, this is basically this is the label encoding part if you want to generalize it for all of our categorical data. And we are assigning categories to it, and we are converting those categories to interpretable number values because the machine learning model can understand numbers. Okay. If there are any missing values, there are none. But if there are any missing values, we can fill it with zero. Okay. Very easy. Now, moving on. These are our independent and dependent features. We know that everything except the sales column will be the independent features, and the sales is our target that we are trying to predict. Okay. Test size standard 20% test, 80% for the training. Random state is equals to 42 for reproducible results. Okay. Now comes the major discussion. Everything is done till now. Okay, it's absolutely clear and it's very important, especially this feature engineering right here. It might even get confusing. Okay, this is good stuff right here. Because real world data is not like Kaggle data sets. It's never clean, it's never easy to work with. In real world, we have to first collect the data, then we have to work with it. So it's never for granted that it's never like written in stone that your data set will be easy to work with. Okay. But we have dealt with the data pre-processing pipeline part. Now we go on to the model. Now, since we have already established that, linear relationships are not really done here because, the sales has a lot of non-linear relationships. We saw that in the correlation heat map as well. So we need to go for some advanced model that captures non-linear relationships. Now, let me quickly, go back if I can show this to you. So on day 8, we basically discussed the XGBoost model. Okay. Basically like a tree ensemble model because it is far more capable of, capturing non-linear relationships. So, I already said that if you have something like a data set having a few million entries and it is large and it has got complex non-linear relationships, you can straight away go for something like an XGBoost. So we can try an XGBoost model here, which we may implement, but is it the correct choice here? The answer is no. XGBoost is not the correct choice here. Okay, so that is what's the main thing that we have to discuss today as part of today's agenda. Till now, it was just sort the pre-processing pipeline and the recap. So, guys, it's very important. Let me start. So, the thing is that XGBoost is a very safe model. Okay. Whenever I'm talking about XGBoost, it always prioritizes safety. Okay. Safety over what? Safety over speed. XGBoost is saying that, okay, I don't care how slow you are in converging, how slow you are in predicting the final results, but my model learning will be very safe. So what happens is in XGBoost is that, it basically prioritizes safety and it grows the trees that we have. It's a boosting model. So it grows the trees level wise. And basically, it is saying I will first grow my trees end to end, then I will calculate the gain values, and then in the last, I will do my final predictions. Okay, this is good. Okay, this makes the model very safe to work with, very conservative, and very dependent. But the thing is, for data sets with the size that we have today, so for the Rossmann data set that we are dealing with today, we have nearly 1 million entries. Okay, we have about 1 million 100,000 entries. So for these sort of entries, these are sort of, low medium kind of data sets. These are not that huge and these are not that small. So if we go for something like gradient boost, okay, which we did on day 8, So if we use something like a gradient boost, it will be too simple for these many entries with non-linear relationships. And it will, definitely underfit. It won't capture the relationships that we require it to capture. And if we use something as conservative as, slow converging as XGBoost, it will be like overkill. Okay. XGBoost will be, like an overkill here. It will be like you are bringing a bazooka to kill a mosquito. Okay, so you have a mosquito roaming around, you're troubling you. You can do this and you will kill the mosquito. There is no need to bring a bazooka. Okay, the XGBoost is like that bazooka. It is only made for, heavy sort of problems where the number of samples that we are dealing with are too many. So can we find something in between? Because this is underkilling. This is not working as strong gradient boosting. And XGBoost is too advanced. So can we find some middle ground where we don't have to be so conservative and still we can be very fast? The answer is yes. That leads us to today's model, which is very similar in nature to XGBoost itself. That model is called nothing but light gradient boosting. Okay. LGBM. Okay. So it is another branch of the gradient boosting models or the boosting models in general. If I quickly show it to you and I write LGBM and show it to you. Okay. So you can read about it as well. Light gradient boosting machine. Okay. So, let me quickly get to it. So LGBM, the thing about LGBM, first of all, is that it prioritizes speed over safety. I will be quickly getting into how the model works, but first look at these things. First, we need to analyze why this is the better choice here. So it prioritizes speed greater than safety. Now, the thing is that, if the model is too fast, it might overfit. Okay. When we are saying speed, we are basically saying that, model is converging very fast. So, model converges very fast, which means that it produces optimal results very fast, which means it will do some sort of optimization, which we will discuss. But when it converges very fast, there's always a risk for noise memorization. It will memorize the noise within the data set and cause overfitting. Okay, which is why it will work in the case of the Rossmann data because we are only have a million entries. If it was some sort of a massive data set, like 10 million entries or 5 million entries, there would have been a greater overfitting risk. But here, that risk is not that significant because our model is not massive. It is of the low medium category, which is why light gradient boosting machine works very well here. Okay. So if I try to, give you the difference between LGBM and XGBoost. So like I said, XGBoost, it prioritizes safety. It first grows the trees entirely. Okay. It goes depth wise and then it says, it calculates the gain using the formula that we discussed. And then it says, what's the value to be calculated here? Then it decides whether the split is worth keeping or not. What does LGBM do? LGBM does not care about depth. Okay, I'll write this down. LGBM grows leaf-wise, not depth-wise. XGBoost grows depth-wise, it grows leaf-wise. What does that mean? Let's say that we have got the tree right here, and the tree is capturing relationships, it is growing. Okay, it is getting updated every step and it is growing. That's how boosting works. Now let's say that we are at this point right here, this point. Okay, and let's say that we are using a LGBM model. So in the LGBM, this node right here, it will calculate the gain at this node, the gain. Okay, and it will basically say, is the gain value the best value that we could have at this node? And if the answer is yes, it will not grow these levels. It will not grow these leaf nodes anymore. It will just say, let's just go this side, and it will grow for this. Then it will grow again for these next nodes by asking this question itself, whether the gain that we are making to ensure the split, is it the best value possible? So it is sort of like a greedy algorithm, like an extremely greedy algorithm, because it's saying, wherever the value is the best, just take me there. I don't care about the other levels. which is why this is very fast to converge. If we were using something like an XGBoost, the XGBoost would be saying that, first grow out all the levels and capture the relationships. Later, I'll calculate the gain, which is the best one. So it will first fill out these levels uniformly. So XGBoost grows level wise or depth wise. It doesn't go leaf wise, whereas the LGBM model, it grows leaf wise. This is why it is faster. Okay. So now let me quickly get back to the report to show this to you. You can read this as you can read this. Okay. It basically explains the same thing, why LGBM is the right fit. Okay. This is a very important table. This is one of the best comparisons you'll find between LGBM and XGBoost. It basically has comparison using a lot of different categories across different categorical values. So you can read this, I'm not reading it. It's just what we discussed right now. Okay. Now, very important, very, very important, what is actually happening in the LGBM. So like I said, the LGBM is quite similar to the XGBoost. So the thing is, the objective function, the loss function that we minimize, it is the same one as we have in XGBoost. Okay. So let me show this to you very quickly. Okay. Let me scroll up and go to the notes of yesterday of day 9. So, this was the value of the objective function. This was the final objective function that we were having for XGBoost. Now for light gradient boosting machine, we have the same objective function. Okay. So it already has all of the strengths of the XGBoost. It is not different at all. I can show it this to you in the repo as well. So if we look at the additive ensemble, this is the same objective function as XGBoost. Exactly the same. Okay. See? The second order Taylor expansion. We did this all step by step yesterday. Okay. So it's the same. See, this is the gain value finally. Okay. So the objective function for LGBM is the same. So what is the thing that actually sets it apart? Okay. You'll ask this, Nasi, because till now, till XGBoost, we saw that it was the objective function that was actually creating a difference. If the objective function is like super optimized and it has the regularization in it, then it actually trains the model very well. It has everything in it. It has inbuilt L2 regularization. It is also checking the split quality. It is using gradients and Hessians to basically optimize everything using Newtonian optimization techniques. But here you'll ask the question that since the optimization is the same, what is actually setting it apart? Now comes, two very important concepts. And this is important because these are like the differentiating features of LGBM. Okay. So I will explain these features. They're very easy to understand. One of them is called as GOSS. Okay, it has a full form. I'll discuss it. And the other is called EFB. Okay, very intuitive to understand both of them. Okay, so we'll go into them one by one. We first quickly open up GOSS. So, whenever we are talking about GOSS, GOSS is nothing but gradient based one sided sampling. Okay. So, what does happen here? So, guys, let's discuss this as intuitively as possible. So, what happens in any algorithm where we calculate the gradient? So, the gradient basically points to the steepest direction of the loss, and our goal is to, reduce that loss as much as possible. So, we calculate the gradient for all the values. So, let's say we have got this graph here and we have got this as the loss function. So, we calculate the gradient at this point. Then we calculate, we take a different color. Okay. Calculate the gradient at this point. Then we calculate the gradient at this point. This is where it's the minimum. We also calculate it here. Okay. We also calculate it here. We calculate it here as well. But is the gradient value going to be the same in all of these points? See, my question is at this point, point A, point B, C, D, E, is the gradient going to be the same in all of these points? No. Why would it be the same? The gradient, if I write it down, the gradient is basically, the slope of the loss function. Okay. So why would it be the same at every point? It is changing now. It is different at every point. So what does this mean? And how do we use it in GOSS? So what GOSS says is that, whenever you are using the gradients to calculate the direction of steepest slope, you're going to get some very high gradient values and some very low gradient values. GOSS is saying that we are going to greedily utilize the high gradient values. Now, why is that? See, if we get a high gradient value, okay, if we get high gradient value, it means that error in that direction is massive. Okay, error is huge in that direction. Okay. Now, if the error is huge, it means that that direction becomes a priority for us to optimize because the error is increasing too much and our goal is to reduce that error. So when we see that the error is too much there, our goal is to reduce it. We try to reduce it. So these massive values of gradients, wherever we get them, they become our priorities. Okay, so that is what we try to, try to use here. We are saying that keep only the higher values of gradients because those are the ones that matter the most. And for the low ones, we do something else. So the Gauss algorithm works something like this. So first of all, sort all gradient values. Okay, and you sort the mod of them because the gradient might be negative in some places, it might be zero, it might be positive. You cannot just take all values straight away at their face value. You need to put a modulus so that the negative values can be brought down to a comparable range. Okay, so you sort all the gradient values. Then step two, you take top a samples of the gradients. A can be any number. Basically, you take top a highest gradient values. Okay. Because they resemble the direction of the highest loss, which is what we need to optimize. And what we do is from the remaining ones, we take only B values of gradient and we upweight them by a parameter. I'll tell you what it all means. It's very intuitive to understand once it all clicks. So what's happening is there, let me like take a list. So I get gradient 1, 2, 3, then gradient 4, gradient 5, and so on. Okay, this is like the list of gradients that I'm calculating at every step for each point. Now I'm saying that the gradients which are the highest values, I'm going to take them as the priority. Why? Because in those directions, the loss is the maximum. So I'm saying keep take the top A values. Now let's say the top A values, let's assume them to be the top three, maybe. So we are taking these top A values as it is. And what to do with the remaining? We are saying out of the remaining, you take the rest of the B values. And, since we are taking only B of the remaining values, we need to weight them in order to, basically account for the bias. See, because we are deliberately going and picking some values that we want. So we are sampling in a way, but we are ignoring the rest of the values. So for that, we need to give some credit. We need to give some bias parameter to these remaining values. And that parameter is, nothing but 1 minus A upon B. So these remaining values, we basically give them this parameter in order to, correct the sampling bias that we just made by selecting it. Okay, this is how GOSS works like. The intuition is very simple, the mathematical intuition. See, you can read it here. So you can say that the highest gradient samples are carrying the maximum information, and that is where the model needs to correct and improve the most. So we take them, and the low ones contribute very little. So we upscale them and we take them with us. And this is the upweighting or upscaling factor that we use. Okay. Now, the EFB, and this is even more important, you can read it alongside as well. So, what happens with the EFB is that, whenever we have real world data sets, we get some mutually exclusive features. What does it mean? Let's say we have got a feature A and we have got another feature, another column B. This has some values and this has some values. Now, it happens in data sets that sometimes A is not correlated to B at all. Okay, which means that changing the values of A does nothing to B and changing the values of B does nothing to A. So these types of features are called as mutually exclusive features. Okay. This is similar to mutually exclusive outcomes that we have heard in probability. Basically two outcomes which have nothing to do with each other. Changing one does not change the other. Okay. These are called mutually exclusive features. So what happens in mutually exclusive features is that, to save space and to reduce dimensionality, we can take both of them and we can merge them. We can merge them into some new synthetic feature C in order to save space. That is it about EFB. And sorry, I forgot to write what is EFB actually. The full form is also, it makes a lot of sense. It is nothing but effective feature bundling. Okay, bundling. So not just a second, I wrote something. Not effective, sorry, not effective, sorry. This is exclusive. Sorry, we are dealing with exclusive ones. Exclusive feature bundle. Okay. So basically, we are saying that whatever the exclusive features are, bundle them up together. And why only the exclusive features? This might be a question. Why not the non-exclusive ones? See, because if any values in this A are related to any values in this B and I merge them together, there will be some overlaps, right? There will be some overlaps in values. And when there are overlaps, the column that we created C, it does not make much sense. See, the point of creating C is we are saying that this is not related to this. So let's just combine them and reduce the dimensionality. But if this is somehow related to this, then there is no point of combining them. Okay, they need to be mutually exclusive in order for us to combine them. Okay, that is the essence of EFB. Okay, so exclusive feature bundling, EFB, and GOSS. Okay, which is basically utilizing the gradient values. So EFB and along with this gradient based one-sided sampling, these two are the things which set apart light gradient boosting machine from XGBoost. Okay, you can read about this here as well. Okay, this is it. So now if I go on to show this to you as to how it works. So let me first go on to the code. First of all, very important thing, guys. This EFB and GOSS, both of these are mechanisms which are happening inside the regressor, happening inside the model. We don't implement them. We are not writing code for EFB and GOSS here. You see, there's no code for EFB and GOSS. It is happening inside this LGBM regressor. Okay, it's a mechanism. So this was, pretty advanced thing to learn from because no one talks about such mechanisms, whereas they are the ones which set these models apart. Okay. The regularization function remains the same. So this is how we train the code. LGBM, since it is similar to XGBoost with the objective function, all of the hyperparameters are the same. We use the same process. We first build a base model, then we use grid search CV to, give the hyperparameter tuning, and we select some values for the tune model, and we get them. So this is for the hyperparameter tuning. We give different values for the parameters, and we basically let grid search CV find out the best set of parameters for this job. Okay. Print it again using grid search CV right here. This is the prediction time that we have printed. Start, this is how you do it. This gives us the best parameters for the model. Okay. We have got the metric comparisons, which I will be discussing. And these are the plots that we print always. Residual errors, then the error distribution in the form of KDE. And this is the feature importance, basically telling us which features were the most important in predicting this model. Now, let me quickly get back to the repo and show you the time and space complexity. So this you can read on your own. It's basically the same thing. Okay. So leaf-wise growth, like I said that the light gradient boosting machine grows leaf-wise, and hence it just goes with the leaf, which gives the highest gain value. It does not care about the depth. So this is like a greedy algorithm sort of a thing. Uh, Works super fast, might lead to overfitting, but we can sort of fix overfitting in here because the data set is not that huge, and we do that with max depth and num leaves. Okay. This is something you can read. So basically, LGBM uses the concept of histogram optimization. So as we discussed EFB right here, So, whenever we do EFB and we bundle these features together, so now the new features are represented in the form of bins. And from those bins, creating splits using the gain formula becomes much more easier because our search space has reduced. Okay, can read this. Now, the time and space complexity. So, guys, originally, when we trained the XGBoost and even the gradient boost, we used to get the time complexity as something like T for the number of trees, N log N for the sorting, then C for the number of times, let's say we have done the cross validation, which we take as 5 or 3, whatever. Then K for the number of combinations of hyperparameters. Okay, so this is the value that we were usually getting. Now in this case, what is happening is that this sorting is not really happening because the splits are created using gain. So the time complexity now becomes T for the number of trees, N for the number of features, C and K are here as it is, but rather we get a new feature or like a new parameter in the complexity, which is called as B. Okay, B. And B basically is the same value that comes to us from the exclusive feature bundling. Okay. And let me quickly discuss as to why this is very good. So if we get back to the repo, can read it as well. So what happens is that whenever we are doing the n log n complexity right here. So n here is nothing but a million. Okay, there are a million samples, which means something like 10 to the power 6. And this is also 10 to the power 6. So this value comes out to be very high. But in this case, we only have n, which means 10 to the power 6. And then we have b, which is the number of bins that we create while doing the histogram binning process. So in the histogram binning, the number of bins that we make is far less than the values of the model. So we have got n as a million, but the number of bins is usually around 255 only. So, this basically contributes to reducing the complexity a lot because B is far less than N. Okay. And this is the exact advantage with the LGBM model. Okay. We are also doing the GOSS where, we are not keeping all of the gradients. We are saying we only want the most relevant we only want the most relevant values of the gradient. So that is even better in reducing the complexity. So instead of n, our value is updated by this. This is far less than n. So this is another way the complexity is getting optimized. Okay. And then we are doing the EFB as well, where the dimensionality of features is reducing because we are combining features, merging them into one. Okay. This is the final time complexity that we are getting. Okay. B is the depth of each tree. You can count it here as well. N is nothing but a million or around a million, whatever are the number of samples. C for the parameter contributions, basically all the combinations in grid search CV. So if I go back here in grid search CV, so this is 2 for the N estimators, 3 for learning rate, 2 for num leaves, and 2 for max depth. 3 into 2 into 2 into 2. So 8 into 3, 24 combinations of model that we are going to be running. So C here is nothing but 24. K is the number of folds in cross validation. We chose it as 5. T is the number of trees. Okay. And B is nothing but, maybe 255 or some other value that we have chosen for the number of bins. Okay. So this value is far less than the value for the one that we get in XGBoost, which is why this is lighter and faster. Okay. This is the prediction complexity. Space complexity, again, we'll be only storing, the features in the bin values along with all of the nodes in the trees. So since the tree scales by 2 to the power n, we get a 2 to the power d complexity here. And we multiplied that by t because we have got t trees. This is the hyperparameter tuning. You can see how it was selected. So this was finally the R2 values that we were getting. This is a very high R2 score, and it means the model has had a very high accuracy. And the tuned model, it obviously runs in a lot less training time. Inference latency is marginally higher. It's fine. Okay. Residual plot, you can see this is the red line around which we compare them. Okay. This is the error distribution. So error is, this is where most of the error is lying between. It means that the model is underestimating the outliers because let's say a value lies here or here. Model will not be able to predict them with high accuracy. Okay. Feature importance. So customers, store and competition distance are the most important features. Can read it. Failure cases, many of the failures are still similar to the ones that we were getting in XGBoost. So extrapolation is still there, because extrapolation basically means that if future sales exceed the old values, then the model will cap the predictions. Basically what's happening is there, let's say in the future we get some very high or very low sales values, but the historical model does not have any value close to it, so the model will take that as an outlier value. Okay. And that will basically lead to very poor generalization in the model. Okay. High leaf count, if there are number, this is always a risk, since light gradient boosting machine is a very aggressive model. It aims for speed rather than stability. There is always a risk for overfitting if the tree is very deep. Okay, so these parameters, num leaves, then num estimators, max depth, they need to be tuned very carefully, because even a slight hiccup in tuning and your model will overfit. Okay. You can read the other ones as well. These are very theoretical values. Okay. These are the key takeaways. Okay. GOSS and EFB are the most important concepts, I will say, from this model itself, because the rest of the stuff was common with the XGBoost. The GOSS and EFB are the most important. So GOSS stands for gradient-based one-side sampling, and EFB is for exclusive feature bundling. These are the two new concepts which set apart the light gradient boosting machine model from XGBoost. Okay. So this is why it becomes very important to analyze everything. See, we couldn't have arrived to this conclusion that LGBM is the model here if we hadn't analyzed everything. So do the processing, the pre-processing, do the EDA, then and only then you will analyze. Okay, it was very easy to just say that the answer is XGBoost here. But since the model size is limited around 1 million training samples and it has non-linear relationships, we can try for something lighter, which is why light GBM is the choice over XGBoost here. You can use this table to, see a lot more interesting comparisons. Okay. And I think this will be it for the repo. You can check out the code. I will leave the GitHub link along with the code link and the datasets in the description. I've also attached two very good articles that you can read for further understanding. The code is all handwritten. It is very, direct to understand. The data pre-processing pipeline today was new. It had a lot of new ideas to analyze. Uh, these notes are all typical. Okay. So I think that is it for day 10. And I will see you tomorrow for day 11 with, let's check out what do we have. Mall customer segmentation using K-means. So this is our first unsupervised algorithm of the entire series that we will be doing tomorrow. Okay. Thank you so much.